Namaste and a warm welcome to one and all. So before we begin, as is the usual practice, let me know if you have any questions with regards to what we discussed in our previous class. Please raise your hand if you have any questions. Okay, so I don't see any raised hands, so maybe we can advance. Okay, so here is a quick summary of what we did last time. Okay, so if you remember, we discussed this idea of a geometric realization of a simplicial complex. Thereafter, we discussed this concepts called as group, field, and vector spaces. So today's focus would be on this idea called as homomorphism. Okay, so homomorphism is a Greek word. Okay, it is made up of two parts. One is homos, and the second part is morph. Okay, so if you sort of look up their meanings on Google, you will find that homos means same and morph means shape or form. So homomorphism loosely means that you have some same shape or same form. So I try to construct the equivalent of this in Hindi, and I encourage you to do it in your own languages if you are interested. So the equivalent would be like saman akar. Okay, so akar means shape and saman means same, right? So I just tried it for fun and I realized that this may be a suitable word for homomorphism, right? So formally, because of this notion, one can interpret homomorphism as a structure preserving map, okay, between two algebraic structures of the same kind. Like for example, we can talk about homomorphism between groups, we can talk about homomorphism between fields, and we can also talk of homomorphism between vector spaces. Okay, so similar to homomorphism, there is something called as an isomorphism. Okay, an isomorphism is a homomorphism where the map is also bijective, right? So in a homomorphism, we only require that the function preserve this algebraic structure. Okay, whereas in an isomorphism, in addition to it being a homomorphism, we also require that the function be a bijection. Okay, so we will look at some specific cases, and hopefully once we discuss them, things will become clear. Okay, so the first thing that we will discuss in relation to homomorphism is that of group homomorphism, right? So what is the group homomorphism? To begin with, we will presume that we are given two groups, right? So when recall what is a group is a tuple, right, made up of two objects. One is a set and the other is the operation, right? So we are presuming here that we have been given two groups over here. So notice that the sets are different, and we can also consider the case that the operations themselves are different, right? And so we have been told that these two objects are abelian groups, and now we have a function h which goes from g to h. So notice that this function h takes as input an element of this set g and spits out another element. Okay, so let's say h of g, which is an element of h. Okay, so it takes an element of g and spits out an element in h. Is that okay? So this is what this function h does. And we will say such a function is a homomorphism if for every pair of element a, b in G, the following relationship holds. Okay, so let's try to understand what does this relationship say. Okay, so there are two inputs that are under consideration here. Okay, so a under h would be mapped to h of a and b would get mapped to h of b, right? So what do we insist? We are insisting that you perform the operation, the group operation on A and B. So notice that A and B belong to G. So indeed, I can perform this operation. So whatever is the result of performing this operation, let's call that as C. Okay, so whatever is the result of performing that operation, we require that when I apply H on the output of A star B, right, the output should equal this relation that is written over here. So notice what is there on the right. The first object over here is the output of A under H. The second object over here is the output of B under H, right? So these are the two things that we have, and we are insisting that the output of H of this C should be H of A times H of B, where this is the operation that is defined in this group over here. So H of A is an element of capital H, H of B is an element of capital H again. So we can indeed perform this operation between H of A and H of B, and we will say H is a homomorphism if for all A comma B, okay, this relationship actually holds true. Is this okay? So let us look at a bunch of examples and then things may become clear. Okay, so first let's look at a very, very easy example. So we have these two groups, Z comma plus, right? So in the first group, the set is the set of integers, right? And the operation is the usual addition between integers, right? So I'm sure, okay, most of you must be comfortable in verifying that this object over here indeed is an abelian group. Okay, on the other side, we have this group E comma dot, okay, where E is made up of elements of the following form, right? So each element over here is E raised to K for some K in the set of integers, right? So the elements of this would, for example, include e raised to minus 2, e raised to minus 1, e raised to 0, e raised to 1, right? E raised to 2, and so on, right? So all possible elements of this kind would be present in this set, right? And the operation that we define over here is the multiplication operation, right? So since this is an exponential function, I hope you agree that e raised to I times e raised to j equals e raised to I plus j, right? So you can see that this again is an element of this set E, right? And you can verify that this again is actually a group, and the identity element is e raised to 0, which is actually 1, right? So I hope you agree that this set along with this operation, okay, this set along with this operation is indeed an abelian group, right? So now we are going to define a function h, right? So what does this function do? It takes as input an integer and spits out an element in E. Is this okay? So it takes an element in the set of integers and spits out an element in E, right? And what is the way it maps the set of integers to the elements in E? Well, the rule is the following, right? So if you give K as input to H, the output would be E raised to K. Okay, so if I sort of write the set of integers here, so let's say dot 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 minus 2, minus 1, 0, 1, 2, and so on, and here let's say I write e raised to minus 2, e raised to minus 1, e raised to 0, which is 1, e raised to 1, e raised to 2, dot dot dot, right? So minus 2 will get mapped over here, minus 1 will get mapped over here, 0 will get mapped to 1, 1 will get mapped to e raised to 1, and so on. Is this okay? So this is how the map h is defined, right? And it is very easy to see that if I take the addition of two integers, right? So addition is the operation. So I take j, perform this operation. So this is the operation that is performed on the set of integers, right? So if I take this, so I hope you agree that because the way this h function is defined, this I plus j under h will get mapped to e of I plus j. Right now, e raised to I plus j is simply e raised to I times e raised to j, right? And e raised to I is h of I, and e raised to j is h of j, and this is the multiplication or the binary operation that is defined on this set. So you can see that if you take two elements from the domain set, right, and perform the operation, and whatever is the result, the output of that thing under h, okay, is the output of you taking the individual outputs, that is h of I and h of j, and performing the operation in set E. Is this okay? So in this case, one can see that H is actually, because it satisfies this property over here, H indeed is a homomorphism, right? In fact, one can show that H is a bijection. right? So one can, I mean, I won't do it, but I'm sure all of you are in fact more capable than me to verify that h, this function h that we have defined over here, is a bijection. By that I mean it is a one-to-one map and onto a surjective map, right? So h is a bijection, and hence it follows that h indeed is a isomorphism, right? So it is not just a homomorphism between these two groups, it's in fact an isomorphism, right? So of course, technically we have sort of talked about homomorphism, isomorphism, and things like that, right? So intuitively, what does it mean? Intuitively, the idea is that although the elements are, the elements in this set and the elements in this set are different, but if you think about it from the perspective of these operations, right? This is just a relabeling of entries that is happening, right? So instead of calling it as -2, I'm calling it as e raised to -2. Instead of calling it as -1, I'm calling it as e raised to -1. And when I perform the operation of addition over here, this is equivalent to performing the multiplication operations between them, right? So isomorphism in some sense means that you have a set along with an operation, you relabel the elements of this parent set, right, and give it new names, right? So here you are giving a new name to -2 and you are calling it e raised to -2. You are giving a new name to -1 and you are the new name is e raised to -1, and so on, right? And if you do the operations, of course the operation is different. However, if you sort of think about it, the operation that you do here is very similar to the operation that we do over here. In that, the output that you get by doing the operation over here is in some sense in correspondence to the output that you would get over here by taking the corresponding elements and performing the equivalent operation, right? So isomorphism or isomorphic spaces, right? So whenever you have a isomorphism between G and H, right? So if H is a isomorphism, we will say that G and H are isomorphic groups. And the intuitive way to think about this is that the elements of H are just a relabeling of the elements of G. Right? This is an intuitive explanation, right? So intuitive means that you can in some sense think of these two groups as one and the same, right? That's the way to interpret it, right? So I would like to sort of elaborate a bit over here. See, when I say two sets are one and the same, right, you have to ensure that the elements of the two sets are one and the same, right? Here we are sort of generalizing this idea of one and the same. Here we are not insisting that the two sets, the two groups, like the sets in the two groups, that is G and H, okay, they have one and the same elements. We are not insisting all those things, right? Instead, what we are saying is that they should behave similarly in the respective operations that we have defined in these two groups. Okay, so that's the idea. Okay, and in that sense, this G and H, whenever they are isomorphic, they are actually, one can treat them as one and the same, right? So now let me give you an example of a homomorphism which is not a isomorphism, right? So in order to define a homomorphism, we need two groups. So the group on the left is again the set of integers along with the usual addition operation, and the group on the right is this set Z2. So recall Z2 is simply made up of two elements, 0 and 1, and that is what I have highlighted over here, right? And the addition over here is the addition mod 2, right? So what this means is that 0 plus 0 is 0, right? And 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0, right? This is the result that you will obtain, okay, by doing the usual addition and then looking at the remainder of that when you divide by 2, right? So this is what addition mod 2 means, right? So now this is one of the groups, this is the second group, okay? And now let us define the function h in the following way, right? So every integer over here is mapped to k mod 2, right? So this is the operation, and you can see that this is actually a homomorphism, right? So you can sort of verify this by checking if h of I plus j is indeed h of I, the mod 2 addition of h of I and h of j. So you can indeed check that, and you can formally verifying by looking at three different cases. Like the first case could be I and j are even, I and j, one of I and j is odd, right? And maybe both I and j are odd, right? So you can consider these three cases, and you can verify that in all of these three cases, this condition actually holds true. And consequently, this function h is actually a homomorphism, right? But I claim that this is not an isomorphism. So this is not an isomorphism because the function h over here is not a bijection. In particular, you can see that this function h is actually many to one, right? So you can see that -1 also get maps to 1 and +1 also gets mapped to 1. So in that sense, you can see that this function h that we have over here is a many to one function, and consequently it's not a bijection, and which in turn shows that this function h is not an isomorphism. Nevertheless, this function h is indeed a homomorphism. And since we are talking about this homomorphism in the context of groups, okay, we can explicitly say that h is actually a group homomorphism. Okay, so let me pause here for a couple of seconds. If there are any questions with regards to group homomorphisms and things like that, this may be a very good place to ask. Let me know if you have any questions. Please raise your hand if you have any questions. Yes, Ramkit, go ahead.
So as you gave the intuition behind homomorphism and then we apply the condition, if it is bijection, then it is known as isomorphism. So what is the intuition behind isomorphism in easy words? Like
I gave actually the intuition behind isomorphism only, right? So I said that so if you see, I presume you are referring to this intuition, is that correct?
yes, yes, yes.
So here actually I spoke about isomorphism. Isomorphism means the two groups are one and the same. It's just that you are viewing at them in a different way. Is that okay? When I say you are viewing at it in a different way, that means that you are giving new names to the elements, and the operation that you perform is, it appears to be that you are doing it in a different way. However, if you think a bit more carefully about these things, you will see that the operation that you perform over here is very similar in spirit to the operation that you perform over here. Is that okay?
Okay, okay, okay.
Okay. So that is the intuition. So isomorphism basically means that if you have a group, I have a group, right? And if the two groups are isomorphic, right? And if we do some operations on my group and if we do some operations on your group, in some sense, we are going to get the same results. Okay, while the labels may be different, right? Like for example, if I take -2 over here and -3, and if I add them, I will get -5. Whereas if I take e raised to -2 over here and e raised to -3 and I multiply them, I will get e raised to -5. Right. So of course, what I got, the result that I got are indeed different. However, you will notice that they are similar in the sense that, the function h actually maps -5 to e raised to -5. Is this okay? So that's the idea that I wanted to stress. Anyways, are there any more questions? If not, maybe we can advance. Okay, so I don't see any raised hands, so maybe we can advance. Is this okay? So all right. Okay, so I was just making sure I have covered everything that I intended to cover. Okay, so the next idea that we will discuss is that of field homomorphism, right? So as I said, see, when I talk about homomorphism, in a broad sense, it means that it is a function between two algebraic objects of the same kind, and this function h should preserve structure. Is this okay? So that's what this broad notion of homomorphism means. So I can talk of homomorphism between groups. I can talk of homomorphism between fields. I can talk of homomorphisms between vector spaces. Okay, so in the same spirit that I spoke about homomorphism between groups, I can now talk about homomorphism between fields. Right. So again, as we saw in the case of graph homomorphism, we need two fields. Is that okay? So let's say the first field is F1 plus and multiplication, right? So this is the field with along with the two operations, right? So remember that a field comes with two operations, and the second field is, let's say, F2 along with these two operations. And again, notice that I'm using two different symbols to emphasize that these two operations need not be one and the same. Okay. Then a function h. So again, notice that h actually goes from the set to this set. Is this okay? So h goes from F1 to F2, and such a function is said to be a homomorphism if it preserves structure. So what does that English phrase mathematically mean? It means that if you perform the addition operation in the domain, that is F1, and you apply h to that, whatever is the output of x plus y, right? The output of h should be h of x plus h of y. So notice that h of x is an element of F2. Similarly, h of y is an element of F2, right? And you are performing the addition operation that is defined under F2. Is that okay? So we require that h of x plus y be h of x plus h of y. Similarly, we require that h of x times y, right? So again, notice that x and y are elements of F1, and I'm using this multiplication operation over here. So I'm performing this multiplication operation, right? And I require that the output of h of x times y be h of x times h of y. Is this okay? So this is what it means to say that H is a field isomorphism, or H, which is a map between two fields, is actually, sorry, I shouldn't say isomorphism. This is what it means to say that H is a homomorphism. Right. So H, which is a function between F1 to F2, is said to be a homomorphism if it preserves structure, which mathematically means that these two conditions are satisfied. Right. So as we saw in the case of graphs, H is said to be an isomorphism if in addition H is also a bijection. Right. So if from F1 to F2, if this map is also a bijection, then we will say that H is actually an isomorphism. So again, one can interpret that although you have these two fields, right, since it's an isomorphism, one can think of these two fields as to be one and the same. Right. It's just you are just relabeling the elements of the field, and you are sort of reinterpreting the operations. However, whatever you are doing is exactly similar to what I'm doing. Is this okay? So that's what field isomorphism means. Okay. I mean, one can cook up examples like in the group homomorphism case, and I encourage you to do that, right? Like when two fields would be isomorphic, when two fields will be homomorphic, and so on and so forth. Okay, but now let's advance and discuss vector space homomorphism, right? So as we discussed group homomorphism, field homomorphism, one can in similar spirit also discuss this idea of vector space homomorphism. So again, on one end, it may appear that, I am sort of repeatedly describing the same thing, right? So some of you may get bored, right? However, you may also be able to appreciate the beauty. The beauty is that, look, homomorphism means structure preserving map, right? So if I had to define a homomorphism between groups, what should this group homomorphism mean? Similarly, I can ask you this question. If I had to define a homomorphism between fields, what should the structure, what should be the structure that should be preserved under this function h? Now, if I'm defining vector space homomorphism, although I have not given you the definition, you should be able to guess, right? And if you understand the underlying philosophy of this homomorphism, tomorrow, if if you manage to cook up some new algebraic objects, right? And if someone asked you, how would you go about defining a homomorphism between these two objects? Again, you can think of, oh, I should somehow ensure that, some structure is preserved, right? So if I want to define a homomorphism between these two new algebraic objects that I have defined, right? A natural definition would be something like this. Right, so you can see that if you understand this concept of homomorphism, you'd be able to define homomorphism in the context of some of the new algebraic objects that some of you may actually go on to create. right? So in that spirit, let's discuss vector space homomorphism, right? So in a vector space homomorphism, as in group homomorphism and field homomorphism, we require two vector spaces. Okay, so the first vector space V1, in the first vector space, the set is V1, the field is F, and the two operations are plus and multiplication, right? So this is the vector addition, and this is the scalar multiplication operation. So I hope you are able to distinguish, the multiplication symbol in the context of a vector space and a multiplication symbol in the context of a field. Okay, so this field itself will come with an addition and multiplication operation. So this addition and multiplication operations that we are defining, these are different to the addition and multiplication operations that may be imbibed or come along with the field. Is that okay? Here I'm sort of being sloppy and I'm saying I represent the whole field just by the set. Okay, so that is just for convenience. However, it must be clear that when I have to talk of a field, I have to talk of the set and the two operations, right? But I'll be a bit lazy here and just denote the entire field by the set itself, right? And these operations actually concern vector additions and scalar multiplications, right? So this is the first vector space. This is the second vector space. So again, you have this set V2, you have this field, the operations defined in relation to this vector space. However, the key thing you have to notice is that the field that we use over here and the field that we use over here, they have to be one and the same, right? So both the vector spaces need to be defined over the same field F, right? So when we want to talk about vector space homomorphism, it is necessary that both the vector spaces be defined over the same field F, right? And now again, I have a function h which goes from this set to this set, right? So h is a function which goes from V1 to V2, and we will say this function h is a vector space homomorphism if it preserves structure. So what does that mean? If you perform the addition operation in the domain, the output of that should be the addition operation in the codomain, right? So h of v1 plus v2 must equal h of v1 plus h of v2, right? And the additions have to be appropriately defined. The addition over here is the addition in the domain vector space, and the addition operation that is defined over here is the addition in the codomain vector space, right? And similarly, if I perform the scalar multiplication operation, so let's say I have V1, I perform the scalar multiplication, right? The output of that under H should be mapped to alpha times H of V1. So notice that I use these different scalar multiplication operation symbols. Okay, so this is the scalar multiplication operation in the first vector space, and this is the scalar multiplication operation on the second vector space, right? And since you want this property to hold, immediately it should be clear why we require that both these vector spaces be defined on the same field, right? Because we want this to hold true, such a relation to hold true, and that can hold true only if this and this, like such an operation can be performed. And for such an operation, for it to be possible to be performed, okay, we require that both these vector spaces be defined on the same field. Okay, and it goes without saying that we require that this relationships be true for all alpha in the field F and for all V1, V2 in the domain V1, right? So these conditions need to hold true for every possible alpha in F and every possible V1, V2 in V1, right? And I won't be proving it. However, it is not very difficult to prove. Okay, one can see that an equivalent condition for these two things to be true is the following, right? So what is this condition? It says that you take this generic form, okay, which is alpha times v1 plus beta times v2, right? So this is you take an arbitrary vector v1 and an arbitrary vector v2, you perform this scalar multiplication operation, then whatever is the resultants, okay, you add those two vectors, and now whatever is the output, h should map this output to something that looks like this. Is this okay? So these are the scalar multiplication operations on the codomain vector space, right? And this is the addition operation. So one can check that these two conditions are true if and only if this condition is true. Okay, and it's not very difficult, and I'm sure each one of you should be able to verify that this condition is equivalent to these two conditions being true. Right now, as soon as you see this condition, okay, a light bulb, a bulb must light in your mind. Oh, this is a condition that we have already seen before, right? So can one of you volunteer and tell me what is this condition and where you have seen this before? Can one of you please volunteer? Have you seen such a condition before? Yes, Jacob.
Is it related to linear transformation?
Yeah, so this is the linearity property. Is this okay? Very good, right? So this is the linearity property. We say that a function h between two vector spaces is linear if this property holds true, right? So although in linear algebra people keep calling this as the linearity property and so on and so forth, right? However, if you look at it from the algebraic perspective, you will see that, oh, this is just a vector space isomorphism property, right? So in linear algebra, people call this as the linearity property. However, in the context of algebra, we will refer to this as vector space isomorphism, right? And again, one can say that if H is a bijection, then H is actually an isomorphism, and the two vector spaces are said to be isomorphic. Is this okay? So here is a quick example of a vector space homomorphism, right? So let Ck be the vector space of all polynomials of degree at most k, right? So these are examples that you must have studied in your linear algebra class, right? So I definitely covered this in the linear algebra class that I taught last semester, right? So let Ck be the vector space of all polynomials of degree at most k. Right, so you can define an addition operation, you can define a scalar multiplication operation, and you can also verify that this is actually a vector space over the set of real numbers. Is this okay? So so let Ck be such a vector space, right? And you define this operator t, right, which goes from Cn to Cn minus 1. Right, and this is the differential operator, and it operates as follows. So let's say I give it a generic polynomial to it. So notice that this is a polynomial of degree at most n, right? So indeed, such a polynomial lies in Cn, and all these a0, a1, so on and so forth, right? They are all real numbers. Is this okay? So this is a representation for a generic polynomial of degree at most n. And this operator is defined as follows. Okay, so let me emphasize that this is the definition, right? So the a0 actually vanishes off. A1 times x will give me a1, and I would have a2 x square over here, and this I will write it as 2a2 x and so on. So I'm just performing the standard differentiation, and this is how this d function is defined. So you can see that if you give as input n degree polynomial, it spits out a polynomial of degree at most n minus 1, and consequently this is an element of Cn minus 1. So if you define this operator in the following way, even if you did not know it was the derivative operator, nevertheless you knew that this is how this operator performs, you can see that D is actually is structure preserving in the following sense. So one can verify that D actually satisfies this property over here, and that is why D is actually a vector space homomorphism. Is this okay? So one can clearly see that it is not an isomorphism. This is because there are some polynomials in Cn that are not there in Cn minus 1, right? And one can indeed see that these two objects are not isomorphic to each other. All right. So let me pause here for a couple of seconds. If you have any questions, this may be a good time to ask. Do you have any questions with regards to this idea of isomorphism and homomorphism and related discussions? Do you have any questions? Please don't think of some questions being trivial. Please don't, think that I am the only one who has questions. Perhaps others don't have questions. Don't think anything like that. If you have a question, just feel free to ask. And please note that, when you ask questions in class, you will immediately get answers. However, if you ask questions outside of office hours or outside of class hours, okay, during those times, I'm quite busy with my other responsibilities and duties. Okay, and often I don't get time to look at your questions and, respond to them, as enthusiastically I can do that now. Okay, so if you have any questions, this may be the best possible time to ask them. All right. So I don't see any raised hands. Okay, so maybe we can advance. Right. So now, as I said, this homomorphism is a very broad term. It just means something that preserves structure, right? And structure, what is a structure and all those things is, defined in the context of this, whatever algebraic object that you are interested in. That is, whether it's a group, whether it's a field, whether it's a vector space, and so on and so forth. So in similar spirit, we can now actually talk about homomorphism between simplicial complexes. Right, so you can see that, just this word homomorphism, right? I gave you this broad idea, and we are now trying to talk about homomorphisms between these different kinds of objects, right? And a simplicial complex is another algebraic object, right? And it also has some property. So let's see, when we would say we have a homomorphism between two simplicial complexes, right? So let K and delta be two simplicial complexes, right? And let V of K and V of delta denote their corresponding vertex sets, right? So we will say a function H which goes from the vertex set of K to the vertex set of delta, right? A function H which goes from the vertex set of K to the vertex set of delta is a homomorphism. So notice that I use this homomorphism loosely, right? Ideally, I should have said it's a homomorphism between the simplicial complex K and delta. To specify that, we are talking of a homomorphism between simplicial complexes and not homomorphism between groups, fields, and so on. However, from the context, it should be clear what kind of homomorphism am I talking about, right? So let's say we have a function H which goes from the vertex set of K to the vertex set of delta, and we will say such a function is a homomorphism if the following property holds. So let's say K, right? K is a simplicial complex, which means that it's a collection of sets. So if V0 to Vd, right? It's a collection of vertices, right? So this is a subset of vertices, right? So this is a subset of V of K, right? So if you have this collection of vertices, so this is a set. If this belongs to K, right? If this belongs to K, then H is a homomorphism. If this belongs to K, implies that if you look at the collection of sets, collection of vertices, H of V0 to H of Vk. So this is a set. This set is also a face in delta, right? So so like let's say D is 1, right? So let's say V0 to V1. If it's an edge in K, then we require that wherever V0 and V1 are mapped, that is H of V0 and H of V1, that should also be a edge in delta. Similarly, if you have V0, V1, V2, if this forms a triangle in K, then we also require that H of V0, H of V1 and H of V2 forms a triangle in delta. Is this okay? And again, one can see that if this H is actually a bijection, then indeed one can claim that H is an isomorphism, and one can then say that these two simplicial complexes are isomorphic. Isomorphic here means that these two simplicial complexes are one and the same, right? And one and the same means that it's just you are just relabeling the vertices, right? However, whatever is the structure that K has, the same structure delta will also have. Okay, so let me know if you have any questions. I saw someone raise his or her hand, but I didn't notice. Yes, Pankaj, go ahead.
Good morning.
Yeah.
I just had this question, like the operation here, is it binary operation or it may be in higher order also?
So if I understand you clearly, you are asking what is the operation in a simplicial complex? Is that your question?
Yes. Yes, right.
So yeah, so an operation means a function, right? So here there is no operation. Is that okay? So we are not performing any operation over here. That's the first thing, right? However, as I said, a homomorphism should preserve structure, right? So here in simplicial complex, the structure is this notion of subsets, right? Like whenever something is there, its subset should also be there, and this simplicial complex is a collection of subsets. Is that okay? So we emphasize that if K and delta are two simplicial complexes, and K is basically made up of these collection of subsets. So if something is a subset in K, we require that the set of vertices obtained under H. Okay, so whatever V0 to Vd get mapped to under H, those collection, I mean that collection is also a face in delta. Is that okay? So you have to sort of come up with this definition. So you can perhaps ask, why is this definition useful? Right? So it's not like some this is a definition that God or somebody came and gave you. This is a definition that people like us have made, right? And why have they made it this way? Because this definition is useful, right? And how is it useful, and so on and so forth, it will become clear through this course. Is this okay? But nevertheless, isomorphism is something that I can immediately tell you. Like if delta and K are isomorphic, then if you sort of know the homology of delta. So let's say you know the homology of delta, and you know that delta and K are isomorphic, right? Then you can immediately conclude that homology of delta and K are one and the same. Is this okay? So does that answer your question partially, Pankaj?
Yes. So is this homomorphism a little bit different from the algebraic homomorphism that we studied?
So you are asking, is this homomorphism different compared to the homomorphism that we discussed in the context of groups, fields, and this? Is that your question?
Yes.
So see, every homomorphism is different, right? Field homomorphism is different to a group homomorphism because we require some additional properties to be true. Is that okay? Right? So broadly speaking, homomorphism should preserve algebraic structure. Is that okay? In that spirit, each of these definitions are similar. However, each of them is different because they are defined in a different context. Is that okay? Right? A simplicial complex doesn't have an operation, so we cannot talk about preserving some operation. I hope that answers your question. Is that okay?
Yeah. Thank you.
Okay. There was one more person who has raised his hand. Was it Sutane? Do you have a yeah? Do you have a question?
Yeah, so in this definition of, say, suppose we assume H is a bijection.
Yes.
Then the definition just says that for every simplex in K, there is a corresponding simplex in delta. But it's still possible that delta has additional simplexes, right? Then,
so in a homomorphism, delta can have additional simplices, but in an isomorphism, that will not happen.
Right, but then it's still a bijection between the vertex sets, right?
So I will actually talk about such a property. Is that okay? Can you just hold on for some time? Is that okay?
Okay, thank you. Okay, thanks.
Okay, so let me just nevertheless emphasize this property. What you are saying is that let's say you have these two simplicial complexes K and delta, and you have a map from vertex set of K to vertex set of delta, right? And you are saying that H could be a bijection, right? H could be a bijection, and you are saying that it could also, H could be a bijection, and also H is a homomorphism. Right? So if I understood you correctly, your issue is that this is just a bijection between the vertices, right? So that's your point, and you are saying that you have a homomorphism, right? So you have a homomorphism, so which means that if you have V0 to Vk, this belongs to K, implies that H of V0 all the way up till H of Vk, okay, this belongs to delta. Right, so you are saying that why should there not be more faces in delta? Is that okay? So we will talk about this.
Yeah.
So we will talk about this. Okay. All right. Okay. Okay. Actually, you are right. Okay. So now that I think of, This is actually a special case of isomorphism. So I also maybe require that the inverse faces. So I also require that. So maybe I'll think about it. Okay, let me think about it, and at the right time I'll answer this question. This is an important question. Maybe so I will sort of put a question mark here. I will think about it a bit more, and I'll get back to you on this. All right. Okay.
Thanks.
Yeah, thanks. That's an important point you raised. Perhaps I'm overlooking something. So when I say it is isomorphic, I indeed require that every face in K is also like the associated to a face in delta, and I also require that every face in delta, if I look at their pre-images under H, right? So that should also be a face in K. So it shouldn't so happen that there are more faces in delta and less faces in K. Right, so what I'm trying to think is that a bijection and a homomorphism, does it automatically require that? If it doesn't automatically require it, then we will have to additionally impose the condition, whatever Sutane just said, that the pre-image of a face in delta should also be a face in K, and only then we will call it as a isomorphism. Okay, so I'll put a question mark here, right? So that's a very important point. I think I sort of overlooked it. Okay, sorry about that, but we will discuss this at some later point. All right. Okay, so now let's introduce this important another important object of interest, which is called as a subgroup. Is this okay? So what is a subgroup? Okay, so I would like to just emphasize what we are trying to do. Okay, so at this point, we are not discussing anything related to simplicial homology. However, in the subsequent lectures, you will see that we will be talking about all these things. Okay, we will be explicitly making use of all these things. Hence, it's very important that we understand what a subgroup is and so on and so forth. Okay, because we'll be making extensive use of these different contexts when we define simplicial homology and so on and so forth. Okay, so hence it's important that we understand these concepts on its own. All right. Okay, so let's look at this another important context called as a subgroup. I noticed that someone has not muted himself. If you are one of them, please mute yourself because I can hear some background noise. Okay, thank you. All right. Okay, so what is a subgroup? So let's say we have been given a group. Okay, so when I say a group, we have been given a set. Along with it, we have a binary operation that is defined, right? And let's say we have a subset H of G. Okay, so we have a subset H of G. So we will say H along with this parent operation, right? So we are not defining any new operation. H is a subset of G. So you look at H along with this operation, right? So we will say this is a subgroup if it's a this is a subgroup of this original group if this itself is a group. Okay, so let me repeat again. Let's say we have been given a group, right? So G is a set. Look at a subset H of G and look at the subset H along with this operation, right? So this is a potential group. So if this indeed is a group, then we will say this is a subgroup. Is this okay? And I will sort of ask this as an exercise, right? So I don't want to derive it in class today, but nevertheless, I'm sure with your background, okay, and understanding of groups and subgroups, you should be able to verify this. Right, so here is the exercise question, and you are supposed to prove it. I'll formally give this as one of the assignment questions, okay, when I later on release the assignment, but nevertheless, let me state it today. Okay, so let's say we have been given a group, right? So one can ask, when is a subset of G along with this operation a subgroup, right? Or when is it a group itself? Right, and one equivalent condition is that these three things hold true. The first is that H is non-empty, right? So why do we require that H be non-empty? Because recall that in every group we need to have an identity element, right? So if you have an empty set, then one cannot talk about this identity element at all, right? Because if you look at the definition of a group, you will see that there exists an identity element which has some desired properties. Right, so if a set is empty, then one cannot talk about whether it's a group or not. Right, so that's why the first condition is that H be non-empty. The second condition is that H should be closed under this binary operation. So closed under this operation means that if I take two elements A and B in H, now notice that A and B is an I mean H is a subset of G, so A and B automatically lie in G, right? So A and B automatically lie in G. So because G is a group, we know that A times B must also be an element of G, right? However, it is since A and B lie in G, lie in H, and H is only a subset of G, it is not necessarily true that A times B also lies in H, right? However, this sufficient condition ensures that H must be closed under this operation, which means that whenever A and B lie in H, their product should also lie in H. Is this okay? So that's what this condition over here means. And the last is that H should be closed under inverses, which means that whenever an element A lies in H, we necessarily require that it's inverse, right? So if you are talking about addition, the inverse will be represented in this way. So we require that this inverse also lie in A and H. And if A, I mean, the operation is multiplicative in nature, then we will say that A inverse should also lie in H, right? So that's what these three conditions mean, right? And the claim is that one quick way to verify whether H is a subgroup or not is that H be non-empty, H be closed under this operation, and H be closed under inverses. So if H satisfies all these three conditions, then indeed H is a group in itself, right? And hence one can think of H as a subgroup, right? So what I would like you to appreciate here is that notice that we don't talk about commutativity, we don't talk about existence of inverse, we don't talk about associativity, and so on and so forth, right? So the claim is that if these conditions hold true, then these associativity, commutativity, identity, existence of inverse, all those things will automatically follow. Is that okay? And that's what I want everyone in the class to actually appreciate, right? We are not talking about this. As soon as we verify these conditions, it automatically follows that H is indeed a group itself. And since H is a subset of G, we will refer to H as a subgroup. Okay, so let me pause here for a second or two. If you have any questions with regards to this part, please let me know. You have any questions? Okay, do you have any questions? Okay, I don't see any raised hands, so maybe I'll advance. Okay, so now let's look at some examples of subgroups. Okay, so here is a group that has been given to us, right? So this is Z8 with addition mod 8, right? So I hope you are able to see that Z8 is basically made up of the elements 0, 1, 2, blah, 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 all the way up till 7. Is this okay? So these are the different elements that are present in Z8. Right? And now let's look at a subset of Z8, okay, which is H is equal to 0, 2, 4, 6, right? So these are the four elements that are part of H. Then H, one can verify that it is satisfying all these three properties, right? And indeed, because it satisfies these three properties, it is a subgroup of Z8. Right, so maybe we can verify some of the properties, right? So the first is we have to verify that it is closed under this binary operation. So which means that if I perform this operation over here, whatever is the result, okay, that should be an element of H itself. So I hope you agree that 0 plus 4 is 4, 4 plus 6. Okay, so this is 10 mod 8, which is 2. So 2 also is an element of H, right? And similarly 6 plus 6. Okay, so this is 12 and modulo 8 is 4, right? So this also belongs to H. So you can see that all these different operations which we can perform between the elements of that are present in H, it is indeed closed under this addition operation. Furthermore, we can check that it is also closed under inverses, right? So what's the inverse of 2? Can one of you please volunteer and tell me what's the inverse of 2? What's the inverse of 2? Can you please raise your hand? I cannot see who is talking. Okay. Okay, I don't see a raised hand, but okay. Yeah, Pankaj. Yeah, I can see it now. Okay, it is 6 because 2 plus 6 is 8 and 8 mod 8 is 0. So this is indeed the inverse of 2 is 6. So you can see that 6 actually lies in this group H here, this set H, and you can see that for every element, that is 2, 4, 6, 0, you can see that their inverses also lie in H itself, right? Like for example, if you look at 4, its inverse is 4. Right, so 4's inverse also lies in H, right? So in that sense, you can see that H is closed under addition, addition mod 8. It is also closed under the inverses, and because of this reason, one can conclude that yes, S is a subgroup of Z8. Okay, so let me pause here. If you have any questions, please let me know. So do you have any questions? Yes, Jacob, go ahead.
How to prove this in a more generic way, like without using examples?
So how to prove this in a generic way? I mean, in this particular case, at least I'm not able to think of how to prove it in a generic way. So your question is to ask, how do I show the inverse of 2, 4, 6, 0 instead of verifying it case by case? Can I show it in one shot? Is that what you're asking?
Yes.
So at least I am not able to immediately think of a way. I think in this case, one will have to go element by element. At least I am not able to think of it. But of course, so let's see if I can think of something immediately. Okay, I'm not able to think of something immediately. If I have some smart way, if I think about it later on, maybe I'll come back to it. Okay, so at this point, I don't have a smart answer. All right. Okay, so let us advance. Okay, so one of the other homework questions that you will have to you'll be asked to do later is the following, right? And we would be requiring this property in the further discussions that we'll be having in today's class. That's why I want to state it here, right? So here is another property with regards to group homomorphism. So let's say there are these two groups, G plus and H multiplication, and let's say H little h is a map between so when I write in this fashion, okay, you have to interpret that H is actually a map from G to H, right? So this is just a shorthand to say that you have two groups and H is a map from G to H and H is a group homomorphism, right? Although I write it in this fashion, it doesn't mean that H actually takes as input element of G and this operation and so on and so forth. So you don't have to interpret in that fashion. H is actually a map from G to H only, right? So the second property is that if you have a group homomorphism that actually goes from G plus to H dot, okay, then one can see that the image of G under H, right? So what is the image of G under H? So image of G is all y in capital H such that there exists x in G and h of x equals y, right? So this is what happens, right? So this is the image of G under H, right? So you sort of ask what are all the elements in capital H that get mapped to from the elements in G, right? So you look at all possible elements in H. So the claim is that this set over here is actually, one can show that this is a subgroup in H, right? So whenever you have a group homomorphism, right, then the image of the domain set, right, that will be a subgroup in H itself, right? And similarly, if you define this kernel of H, right, so let's try to understand what is the kernel of H. So the kernel of H is defined in the following way. It is the collection of all elements in G, which is the domain set, which get mapped to the identity element in H, right? So this is the identity element in H, okay? So I hope you agree that this kernel is a subset of G, right? So there is a typo here. So one can verify that, that the kernel of H is actually a subgroup in G itself. Is this okay? So one can actually verify this. So this will be one of your questions in your assignment. Okay, so one should be able to verify that if H is a group homomorphism, then the image of G under H is a subgroup in H, and the kernel of H is actually a subgroup in G, right? And one will, I mean, there will be one more question that I'll be asking as part of your homework, which would go as follows. Right, let G comma star and H comma multiplication, okay, this be two groups, and let's say H is an isomorphism, right? So let's say H is an isomorphism, right, which means that it is a homomorphism and it's a bijection between these two groups. Then one can indeed show that the inverse of this function, right, between which goes from H to G. Right, so first thing you have to ask is the inverse defined? Right, well, since H is a bijection, which follows from the fact that H is an isomorphism, then it indeed is the case that the inverse exists, right? And the inverse will go from capital H to G. And what this theorem is saying is that if H is actually an isomorphism, then H inverse is also an isomorphism, right? So H inverse is also an isomorphism. Okay, so H inverse is also an isomorphism, right? Okay, so let me pause here for a couple of seconds. So if you have any questions with regards to the statements in these two questions, okay, these will be asked. I mean, you'll be asked to prove this as part of your first assignment, right? If you have any questions, please let me know. I'd be happy to answer them. If there are any things, if there is any concept that is not clear to you and so on and so forth, this may be a good time to ask. Okay, so I don't see any raised hands, so maybe we can advance. All right. Okay, so as you have seen, this concept of a subgroup, we can also talk of the concept of subfields and subspaces. Okay, by subspaces, I mean actually sub vector spaces, right? So this is a subset of a vector space, which is itself a vector space. So these concept of subspaces you must have already studied when we were doing linear algebra. And similarly, one can define what are called as subfields, right? So these are subsets of fields which are under the operations of the parent field. One can view this subset along with this operation of a parent field as a field itself, right? So in that case, we will call this subset as a subfield, and one can show that these three properties, okay, whatever we have stated as part of homework 1, homework 2, and homework 3, okay, so you know, these three properties actually hold true in the context of subfields and subspaces as well, right? And since I'm making a very you know, general statement over here, let me verify one such statement in the context of vector spaces. Okay, so here is a statement which is very similar to what we have in the context of groups, but we will state it now in the context of vector spaces. Okay, so what is the claim? The claim is the following: let V and W be two vector spaces, okay, and we will presume that these two vector spaces are defined on the same field. Okay, so let V and W be two spaces defined over the same field, F. Right, so this is something we will presume. And suppose we have been told that T is a vector space isomorphism. This means that T is actually a bijection from V to W. Furthermore, it is the case that T is a vector space homomorphism, right? And what we have asking to verify is that T inverse, which goes from W to V, is also a vector space isomorphism, right? So this is in similar spirit to this homework 3 that we had, where we said that if H is a group isomorphism from G to H, then so is H inverse, right? So here in similar spirit, what we are saying is that if V and W are two vector spaces defined over the same field F, and T, which goes from V to W, is a vector space isomorphism, then so is T inverse. Is this okay? So in order to verify that T inverse is also a vector space isomorphism, right, we need to verify two things, right? So the first thing is that T inverse is a bijection, and the second thing is that T inverse is a vector space homomorphism, right? So it's actually a vector space homomorphism. All right. Okay, so this is what we are supposed to verify. So let's verify them. Okay, so the fact that T inverse is a bijection is a trivial conclusion, like a trivial statement, because T itself is a bijection, right? So whenever T is a bijection, it automatically follows that T inverse, this is the inverse of this T map, right? So this inverse of this T map actually exists whenever T is a bijection, and T inverse it's also 1-to-1 and onto. Right, so because of this reason, it trivially follows that T inverse is a bijection, and hence it suffices to verify only the second part, that is T inverse is a vector space homomorphism. Right, so what does that mean? Right, how do we verify that T inverse is a vector space homomorphism? We need to verify that if W1 and W2, right, if W1 and W2 are two elements of capital W, if W1 and W2 are two elements of capital W, and let's say alpha 1 and alpha 2 are two elements of this field F, right? And if you look at this linear combination of W1 and W2, and if you apply T inverse over that, we will say T inverse is a vector space homomorphism if this relationship holds true, right? That is alpha 1 times T inverse of W1 plus alpha 2 times T inverse of W2. This must equal this. Okay, so here I would like to highlight one part. So ideally, this scalar multiplication and this addition over here, right, those are different in nature to the scalar multiplication and the addition operation over here. However, I am now being sloppy and I'm sort of using the same notations, right? This is on purpose. This is because I don't want to unnecessarily complicate the symbols and so on and so forth, and it becomes in the long run harder to read what is being said, right? However, since by now you should be familiar with what is a vector space and so on, whenever I talk about scalar multiplication and addition, you have to be careful, right? The scalar multiplication that is being performed over here is the operation in W, because W1 is an element of W. Right. Similarly, this addition operation that I'm performing is the addition that is defined in the context of this vector space W, because alpha 1 W1 and alpha 2 W2 are elements of W. Okay, so that's the way you will interpret it. On the other hand, here T inverse of W1 is an element of V. So this is a scalar multiplication in the V vector space. Similarly, this is the scalar multiplication in the V vector space. And finally, this addition operation that you have over here, okay, this is the addition operation in the V vector space. Okay, so although I use the same symbols, I'm overloading the symbols. This is just to make sure the the notations and all those things do not get unnecessarily complicated, right? And also the interpretation over here is unambiguous, that okay, these are elements in W, so this scalar multiplication should be from W. This addition should also be from the perspective of W, right? So there is no ambiguity. You cannot interpret this addition from the V vector space. Why? Because these are not elements in V. Okay, so I hope that is clear. So this is what we need to verify in order to check if T inverse is indeed a vector space homomorphism or not. Okay, so let's do that verification. Right now we know that this T is a bijection. Right, since we know T is a bijection, I hope you agree that there exists vectors V1 and V2 in V such that T of V1 is W1 and T of V2 is W2. So I hope you agree with this part, right? Okay, sorry. Okay, so since T is a bijection, it follows that T of V1 equals W1 and T of V2 equals W2 for some V1 and some V2, right? So I can write this entire expression, okay, as alpha 1 T of V1 plus alpha 2 T of V2. So I have copied this alpha 1 directly over here and this W1 directly over here. Similarly, I have copied this alpha 2 over here and this W2 directly over here, and I write this expression, which is exactly this. Right now, since T is linear or T is a isomorphism, and which in turn implies that T is a homomorphism, which is equivalent to saying that T is linear, this entire expression I can write it as T of alpha 1 V1 plus alpha 2 V2. Right, so I can write it in this fashion, and now from the property that T is a bijection, and since this inverse is defined, I hope you agree that if I take alpha 1 V1, look at its output under T, and whatever is the output, if I apply T inverse, since these are bijective maps, I would get back the original expression, that is alpha 1 V1 plus alpha 2 V2. And now I remember that V1 is just T inverse of W1 and V2 is just T inverse of W2, right? So I have verified that this expression over here equals this expression, and from this I can verify that T inverse is indeed a vector space homomorphism, right? Is this okay? And because of this reason, since T inverse is also a bijection, it immediately follows that T inverse is a vector space isomorphism. Is this okay? So this completes the proof that if T is a vector space isomorphism, then so is T inverse. Okay, so let me pause here for a second or two. If there are any questions, please let me know with regards to this proof. Do you have any questions? If there are any questions, please let me know. Okay, I don't see any raised hands, so maybe we can advance. Okay, so an interesting remark. Okay, and I also had a chance to think about what Sutane said. Okay, so I realized that I was wrong above. Okay, so I will talk about that now. Okay, so here is an interesting remark, right? So what is this interesting remark? In the context of groups, fields, and vector spaces, although we did not prove it explicitly for groups and fields, but we proved it explicitly in the context of vector spaces, we notice that whenever H is a bijective homomorphism, then it automatically follows that the inverse is also a bijective homomorphism, right? So let me repeat, in the context of groups, fields, and vector spaces. So we did not prove it for groups and fields. We just stated it, but we proved it explicitly in the context of vector spaces. We verified that if H is a bijective homomorphism, then its inverse is automatically a bijective homomorphism, right? However, in the context of a continuous function between topological spaces and also between functions from v of k to v of delta, right? Like functions between vertices of two simplicial complex, as Sutane pointed out, right? It is not necessarily true that if H, right, if H is a bijection, okay, and a homomorphism, right, then the inverse, okay, that is H inverse, which goes from v of delta to v of k, okay, is also a homomorphism, right? So one can think of a very simple example. Okay, so here is an example, right? So let's say k over here is made up of two vertices v1, v2. That's it. Okay, the simplicial complex only includes these two vertices, whereas delta, let's say, includes a, b, and let's say a, b, right? So it includes these two vertices a and b, and it includes the edge ab between them, right? So as Sutane found out, okay, so let's say this is v1, this is v2, and this is ab over here, right? So v1, let's say, is mapped to a and v2 is mapped to b, right? And one can clearly see that this function h that we have over here, okay, this is a bijection between the vertex set of k and the vertex set of delta, right? And you can also see that this is a homomorphism between the simplicial complexes, right? So since k only consists of these two faces, that is v1 and v2, right? One can clearly see that if v1 is a face, h of v1 is also a face. Similarly, since v2 is a face, h of v2 is also a face, right? However, the H inverse map is actually not a vector space, a homomorphism between the simplicial complexes, since H inverse of so let's be careful. So you have this edge AB. Okay, so this is a face in delta, and H inverse of A, comma H inverse of B, this is not a face in K. right? So because of this reason, H inverse is not a homomorphism between between delta and K, right? So the condition for isomorphism should be as follows, right? So H, which is a map from V to K, okay, V of K to V of delta. This is a homomorphism if V1, V0 to let's say Vd lying in K implies H of V0 all the way till H of Vk lies in delta. This is the first condition, right? So isomorphism. When is H said to be an isomorphism? Well, the answer is that it should satisfy these three conditions. So the first is this. The second is that H is a bijection, right? And the third is that, so I'll put a condition over here. So this is to be read as if and only if, right? This is to be read as if and only if, right? So H is said to be an isomorphism between two simplicial complexes if V0 to Vd lies in K, if and only if H of V0 to H of Vk lies in delta, and furthermore this H is a bijection, right? So if these two conditions are true, then one can conclude that indeed H is an isomorphism and these two simplicial complexes are isomorphic. Okay, so Sutane, I hope this answers your question.
Yeah, thank you.
Okay, so thanks for pointing that out. Okay, and indeed one can see that this is there. Okay, so why am I raising this, right? So let me sort of connect it back to what I was saying, right? In the context of groups, fields and vector spaces, whenever you have a bijective homomorphism, the inverse automatically is a bijective homomorphism, right? Let me repeat. In the context of groups, fields and vector spaces, whenever you have a bijective homomorphism, its inverse is also a bijective homomorphism, right? However, so that's why whenever we have a bijective homomorphism, okay, we call this as a isomorphism. Is this okay? However, as we saw in the context of simplicial complexes, a bijective homomorphism, okay, does not automatically, I mean, its inverse is not automatically a homomorphism, right? So that is not automatic. Hence, in the definition of isomorphism, we have to explicitly include that the inverse is also a homomorphism. Is that okay? So this part that I have drawn over here, you can see that there is a double arrow which implies that this is true if and only if this is true, right? So that additional part needs to be emphasized, and only then one can show that this map is actually an isomorphism between two simplicial complexes, and finally K and delta can then be thought of as isomorphic simplicial complexes. Okay, so such a thing also holds true in the context of continuous functions that are defined between two topological spaces, right? So what happens there is that a continuous function that is bijective, okay, is not automatically does not automatically imply that the inverse is also continuous. Let me repeat. Let's say you have two topological spaces and you have a function which goes from one topological space to the other, and let's say that function turns out to be both bijective and continuous. So these two conditions do not automatically imply that the inverse, right, is also continuous, right? So it is because of this reason that when we actually talk of homeomorphism or topological isomorphism, right? So if you sort of remember in the first lecture or so, when we talked about homomorphism, and if you look at the definition there, we insist that the function should be continuous, it should be bijective, and the inverse should also be continuous. Okay, so this in similar spirit to what we talked over here. Okay, so this function over here should satisfy this property, it should be a bijection, and the inverse should also satisfy this property. Okay, so that's what we are emphasizing. Okay, so in the context of group fields and vector spaces, a bijective homomorphism automatically implies that the inverse is also a bijective homomorphism. That is not the case in the context of continuous functions between topological spaces or functions between simplicial complexes. So when we have to talk about isomorphism, we have to explicitly emphasize that the inverse satisfies some additional property. Okay, so let me pause here for a couple of seconds. If you have any questions with regards to this remark, this would be a great time to ask that. Let me know if you have any questions. Okay, so I don't see any raised hands, so maybe we'll advance and move on to the last topic of the day, okay, which is that of direct sums. Okay, so what is the direct sum? First, let's try to understand why is this idea of direct sum needed, right? So the idea of direct sum is needed because it is useful to create new algebraic objects using existing algebraic objects. Okay, so if you had some existing algebraic object and you wanted to create something using that, and such that some similar properties hold true in the new object as well, then you make use of this concept of direct sum, right? So let me explain this in the context of groups, okay, and one can similarly define it in the context of vector spaces as well. So let's try to understand what is the direct sum of group. Okay, so to begin with, we will presume that we have been given two groups and we will presume that these are abelian groups. Then their direct sum is the group. So whenever I talk about a group, I have to give you two things. One is the set and the operation, right? So the set here is denoted in this fashion. So notice that you take G and H and in some sense you combine this set, right? And then you define this new operation, and I'll talk about what is this set and what is this operation, right? So what is this set? Well, this set now includes vectors of size 2. Okay, so observe that the first element is G and the second element is H. The first element is taken from this group capital G and the second element is taken over here from this group capital H. Right, so G direct sum H, the elements of this are tuples of size 2 or ordered lists of size 2, where the first element comes from G and the second element comes from this capital H. Okay, so I hope this is clear. And now I have to talk about the operation, right? So the operation is defined as follows. So let's say you give me two elements from this direct sum. So let us denote them as G1 H1 and G2 H2. And now you perform this operation over here. So what is this operation? How do you do it? So now notice that G comes with this operation plus and H comes with this operation multiplication, right? So what you do is whenever you have to perform this new binary operation, the way to perform it is you take this G1 and G2 and perform the corresponding operation that is defined in G. Now notice that G1, G2 lie in capital G, hence you can perform this operation. Similarly, you take H1 and H2 and performing the corresponding operation. Now notice that since G1 and G2 are elements of G, if you perform this operation, the output will also be an element of G. Similarly, if you take H1, H2, perform this operation, they will lie, the resultant will lie in H. So I hope you agree that this lies in G, this lies in H, and hence this tuple or this ordered list lies in G direct sum H. Is this okay? So that's what direct sum is all about. Okay, so you have two groups, you combine and create this new set over here, right? And you define this new operation over here, which is this new set, and this new operation is defined in this way. So I hope you now agree that I can now talk about, let's say G1, G2, G3 are three groups. I can actually talk about G1 direct sum, G2 direct sum, G3. Right, so you should be able to generalize this idea that I have spoken over here and be able to construct this direct sum of G1, G2 and G3. Similarly, you can take G1, G2, G3, G4 and construct their direct sum. And in this sense, I hope you you are now familiar and capable of constructing direct sums of as many groups as given. Right, and in similar spirit, one can also talk about direct sum of vector spaces. The idea is the same. Right, so let's say we have been given these vector spaces V1 to Vk, and again I emphasize that all these vector spaces are defined over the same field, and let's say the field is denoted as F, right? And now I want to talk about the direct sum of these K vector spaces. Well, again, I have to first define a set, right? So what is the set? Well, it is defined as the direct sum of V1, V2 all the way up till Vk, right? So now I claim that this also is another vector space. So whenever I claim this, your question should be, please give me the addition operation, the definition of the addition operation on this new vector space or on this new set, and also give me the definition of the scalar multiplication. Well, I'm going to now talk about the addition in this new set and the scalar multiplication in this new set. Okay, so let's first understand what this set is. It is it consists of ordered lists of size k, where the ith element comes from capital Vi. So let me again repeat. So we have been given these k sets. I look at the direct sum. What is the direct sum? The elements of the direct sum are ordered lists of size k, and the ith element comes from capital Vi. So these are little v1, little v2, all the way up to little vk, and little vi, which is the ith element, that comes from capital Vi. So this is the set. Now let me talk about the addition operation, right? So you give me two elements from this set. So let's say the first element is v1 to vk and the second element is w1 to wk, and now I have to add them, right? So the addition is defined coordinate wise. So I take v1, I add it to w1. Now notice that v1 and w1 lie in capital V1. So this addition over here is the addition defined with respect to v1, right? Similarly, you have v2 and w2. So those two elements lie in capital V2. So I add them according to the addition operation defined in v2. And finally, I take vk, wk. These are elements in capital Vk, and I can define this addition operation. Now again, I emphasize, while I use the same symbol over here, okay, this symbol is for this vector space. This symbol is for this vector space V1. This symbol over here is for the vector space Vk. So I have been sloppy here using the same notation. However, you all should now be capable of distinguishing when each symbol means what. Is that okay? And finally, I have to do the scalar multiplication operation. So alpha is an element of F, right? So this is this field F, which is the common field for all the vector spaces V1 to Vk. So alpha times V1 to Vk. So I take an element in V. I want to multiply it with this scalar multiple. Well, I do it in the following way. So each individual element is multiplied with alpha. So this is the scalar multiplication of alpha and V1. This is defined in the context of this capital V1 vector space. This is defined in the context of this capital V2 vector space, and so on, right? So in this sense, I have defined the scalar multiplication and the addition operations, right? So in fact, one can show that the R2 Euclidean space that all of you must be familiar with can be thought of as the direct sum of R over R, and one can think of R as a vector space over R itself, right? So R is a field, and you can also think of R as a vector space over this field R, right? So this also is a vector space over field R, and you can think of R2 as the direct sum of R with itself, and this is also a R vector space. Okay, so this sort of brings me to the end of the class. So let me stop over here and stop the recording. If you have any questions, I'll be available for some more time, and you are free to ask me any question.